Hello and welcome to STAT 441 at Virginia Commonwealth University. This lecture covers 4.1 through 4.3 from the textbook, and we will be discussing what discrete random variables are and their probability distributions. So far in chapters 2 and 3, we've learned about variables. We know variables can be discrete or continuous. And then in chapter 3, we learned some basics about probability. Now let's put both of these together and discuss a probability distribution for a given random variable. So let's first define our random variable. We will define our random variable with the uppercase Y. In this case, it could be X or any other alphabet. So we'll define our random variable over a sample space. Let's say this is the sample space. Then each simple event is a value that this random variable can take. Now, depending on the sample space, this random variable could be discrete or a continuous random variable. So in this chapter, we will discuss cases where the variable that we have defined over this sample space can take only discrete values. And in the next chapter, we will discuss the case when the random variable is continuous. That means it can take infinite values on the number line. For the discrete, it can take only specific values over the number line. So for our discrete random variable, y, we will assume that it can take only countable number of values, just like how we've defined the discrete variable. Now, these discrete values that this distribution can take now will be only non-negative integers, and the value of y can be 0, 1, 2, it can go all the way up to infinity, but it has to take some countable values. It cannot take decimal values, and it cannot take any negative values. In this chapter, we will discuss various experiments which can take these discrete values, and there are various discrete random variables that we can define and the probabilities associated with that. So we will look at a few distributions like the binomial distribution and the Poisson distribution. There are other distributions that can be defined. So our experiment can be in the form of one of these distributions, and we can describe the probabilities of the variable. So let's start with just discussing a discrete random variable in general, and then we will look at specific distributions in the next few lectures. Okay, so let's assume that we have a random variable y, which can assume numerical values, and we want to calculate the probabilities of these numerical values or the numerical events. So the convention that we will use here will be uppercase letters will be denoting our random variable. The lowercase letter, so in this case, uppercase y is our variable. The lowercase y will be the numerical values that this random variable can take. So let's say the values that y can take are 0, 1, and 2. Then the lowercase y will be 0, 1, or 2. Okay. When we want to write the probability, we can write the probability in this format: probability of y equals y, where y is the possible value. Okay, so let's put this together. So we will use this notation: probability of y equals y. And we can also simplify this by just using the lowercase y. So let's say the value of y is 2, so we can just say probability of 2 instead of saying probability of y equals 2. So that will just simplify the notation. Okay. Now, since this is a probability distribution, it will satisfy the rules of probability that we have seen earlier. So the first rule is that the probability of any value of y can be between 0 and 1. It cannot be a negative number. It cannot be more than 1. And the second rule is that the total of all probabilities for the given values of y for this discrete variable has to be equal to 1. It cannot be less, it cannot be more. So the sum, the total probability has to be equal to 1 for the combination of all possible values of y. Now let's think of an experiment, a very simple one. We have seen that in the past. And this time we want to define the probability distribution as a discrete random variable. So let's say we have a balanced coin which is tossed twice, and we define a random variable y, which is now the number of heads observed. So think about this. What we want is we want this variable y to take only discrete values. We want numerical values for this variable y. So in this experiment, what we will do is we are counting the number of heads. Okay. And then we can also describe the probability distribution of this variable y. So let's see how this will work. So if you think of the tossing a coin 2 times or tossing 2 coins, the possible outcomes are that we get both tails, heads, tails, tails, head, or heads, heads. So what we do is we change these outcomes or display these outcomes in form of discrete numbers. So tails, tails means no heads, so we'll use 0 for that. Then heads, tails, or tails, head means there is 1 head in this outcome. And then HH will be 2 heads. So 0, 1, and 2 will now be our discrete random variable. And then we have to describe the probability distribution of this discrete random variable, which can take values 0, 1, and 2. Okay, so what we have done here is we have transformed our sample space to a discrete random variable, and then we want to describe the probability distribution. So let's describe the probability distribution by first setting it up. So let HI and TI denote the observation of a head or tail respectively on the first try or the second try. The 4 simple events and the values associated will be given on the next slide, but we have already seen that the values will be the number of heads, which could be 0, 1, or 2. Okay, so let's see how it will look like. So the simple event, the first one is H1, H2. That means heads on the first one, heads on the second try. Its probability is 1/4, and the value of the variable y is 2 in this case because you're counting the number of heads. Then these 2 simple events here, E2 and E3, we have H1, T2 and T1, H2. So first head, then tails, first tail, then heads. Either way, the probability is 1/4 and 1/4, and the value of y for both is 1. The fourth possible outcome is T1, T2. Probability is 1/4 and y is 0. So when we're describing a discrete random variable, it can take 3 possible values. Probability of y equals 0 is 1/4. Probability of y equal 1 is the sum of these two. Okay, so 1/4 and 1/4, 1/2. Probability of 1 is 1/2. Probability of y equals 2 is 1/4. So we can rewrite this in this format. Probability of y equals 0. See, this is the simplified form. Probability of 0 is 1/4. Probability of 1 is 1/2. Probability of 2 is 1/4. There are multiple ways in which we can write the distribution of our discrete random variable. This is one way to do that. The other way is to write it in the form of a small table. So y is equal 0, 1, or 2. Probability of y is 1/4, 1/2, and 1/4 corresponding to the values, and the sum of all y's is equal to 1. We can also display the probability in the form of a graph. So here you can see the three possible values are 0, 1, and 2. And on the y-axis, we have the probability. So 0 and 2 have 1/4, and in the middle, 1 is 1/2. Okay. So what we just did was we took a sample space which was non-numeric, but we converted that sample space into a discrete random variable, and the probability distribution was defined in the form with the values of the discrete random variable. So this was, in general, what a discrete random variable distribution looks like. Okay, let's look at a couple of more examples to understand in general the idea of a discrete distribution. So in this example, the National Highway Traffic Safety Administration has developed a driver's side star scoring system for crash testing new cars. Each crash tested car is given a rating ranging from 1 star to 5 stars. And the more stars in the rating, the better the level of crash protection in a head-on collision. Okay, so now if you think of this experiment, the discrete random variable is the number of stars, and the possible values of this discrete random variable is 1, 2, 3, 4, or 5. Okay. Here's the information that we have. Assume that one of the 98 cars selected at random, and let y equal the number of stars in a car's driver's side star rating. Use the information in the table to find the probability distribution for y, and then find the probability that y is less than equal 3. So we have information about these 98 cars. Let's see what it looks like. Okay, so here is the star rating and the count and the percentage. Okay, so this is like a frequency distribution. So the rating is 2, 3, 4, or 5. So there is no car with a rating of 1. So probability of 1 is just 0. Then for the rest, this is what we have. 4 cars, change it to percent, 4.08. For 3 stars, 17.35. 4 stars, 60.20. 5 stars, 18.37. So we can change this to a probability like this. Probability of 2 is 0.0408. Probability of 3 is 0.1735. Probability of 4 is 0.6020. And probability of 5 is 0.1837. If you add these, you get a sum of 1. That means these are the total probabilities. There cannot be a star rating outside this 2, 3, 4, or 5. There is nothing with 1, and you cannot have more than 5 stars in this example. Okay, now if we had to give the probability distribution, this is what it would look like. We can state the probability here just like this. Probability of 2, 3, 4, and 5, and this is our probability distribution for the number of stars. Now, it's a discrete probability. So if we wanted to find the probability of y less than equal to 3, we simply have to add the probability of the stars being 1, 2, or 3. Obviously, there is nothing with 1, so it's basically adding the probabilities of 2 and 3. Okay, so notice the sign here, it's y less than equal to 3. That's why we have included 3. If the question asks what is the probability of y less than 3, then 3 is not included, and we only have the probability of 1 and 2. Okay, now what we have seen here is that we have a discrete variable, and it's similar to the data that we had seen earlier. So when we have data, especially in cases of engineering and sciences, or scientific processes. For example, in quality control, a production process is monitored and the number of defective parts produced per hour is recorded. Okay, so this type of data we have seen could be described using some of the numerical descriptive measures such as mean and the standard deviation. Now what we'll try to do is for our random variable that we have here with the probability distribution, we will try to find the mean and standard deviation with the use of the probability distribution. Okay, so let's first look at the mean or also called the expected value of our variable y. Okay, so we have to use the probability distribution of this discrete random variable to get the expected value or the mean. And here is how we solve it. So mu is equal to, this is expected value of y, uppercase E, and then square brackets, and then our variable y. So this is called expected value of y. It's equal to the mean, and it is equal to the sum of each value of y times this probability. So it's kind of a weighted average or the weighted probability that we are using. So a value of y which has a higher probability will have more value or more weight here, and then something with smaller probability will have a lesser weight. So y times its probability for each value of y, and then we add that up. That gives us the expected value or the mean of our discrete random variable. We can also find the variance in standard deviation of our discrete random variable. So it's sigma square for the variance. And then the way we calculate this is called the expected value of y minus mu whole squared. Another way of writing this is expected value of y squared minus mu square. And in the next slide, we will see how to solve this. Standard deviation is simply the square root of the variance. So again, we can find this using the same formula. Okay, so let's try this. Let's calculate the mean and standard deviation for the car data that we just saw with the star rating and the distribution. We want to find the mean, star rating, and the standard deviation for a variable y. So first let's calculate the mean. Mean is expected value of y, and it is the sum of all y's times its probability. So we have 5 stars here, with the first one being 0. So y equals 1 through 5. 1 times 0 plus 2 times its probability plus 3 times its probability plus 4 times the probability of 4 and 5 times the probability of 5. So the average rating, average star rating comes out to be 3.93. So this is like based on the probability distribution. So since 4 is the highest probability, so this will have the most weight, and this has no weight, and then these are less than 4. So as you can see, the mean is close to 4 because that has the highest weight. Okay, now let's look at how to calculate the sigma square or the variance. So it is expected value of y minus mu whole squared. So what we do is we take each value of y and subtract the mean from that, square it, and times its probability. So it's kind of similar to how we calculated the variance in chapter 2. So take the value of y, okay, so 1 minus 3.93 whole squared times 0, which is the probability, plus 2 minus 3.93 whole square times its probability, 0.0408, plus 3 minus the mean whole square times its probability, and similarly for 4 and 5. That will give us 0.51 as the variance, and the standard deviation is square root of 0.51, which is 0.714. Okay. Now these distributions, we can also use the empirical rule and figure out the probability that falls within a certain interval, mu plus minus sigma, mu plus and minus 2 sigma, so on and so forth. So let's say we wanted to find for the crash rating, what is the probability that a value of y will fall in the interval of mu plus 2 sigma. So in this case, we already have the probability distribution. We need to figure out what are the values for mu plus and minus 2 sigma, and then we can simply add the probabilities for that range. So mu plus 2 sigma in this case is 3.93 plus and minus 2 times the standard deviation. Okay, so that gives us an interval of 2.51 through 5.35. Now, if you think about the values of the star rating, it could be 2, 3, 4, or 5. So basically, it is only discrete values. It cannot take these decimal values. It cannot be 2.51 or 5.35. So what we will do is, using these numbers, we will pick the values that fall within the interval. The values that fall within the interval that we have created. Okay, let's look back at it. 2.51 and 5.35. So the values of the star rating that falls within this interval is 3, 4, or 5. Okay, so the probability that a value will fall within mu plus and minus 2 sigma is that it's either 3, 4, or 5. Okay, and we add the probabilities of 3, 4, and 5. So 0.1735 plus 0.6020 plus 0.1837. Okay. Here is another example. A panel of meteorological and civil engineers studying emergency evacuation plans for Florida's Gulf Coast in the event of a hurricane has estimated that it would take between 13 and 18 hours to evacuate people living in low-lying land with the probabilities. And here are the probabilities given to us in the next slide. We want to calculate the mean and standard deviation of the probability distribution of the evacuation times. And we want to figure out within what range would you expect the time to evacuate to fall. Okay, so here is the distribution, evacuation time, the nearest hour, and its probability distribution. So here you can see 13 hours, 4%, 14 hours, 25%, 15 has the maximum of 0.4, and then again it decreases. So we need the mean and the standard deviation first. So mean is mu, expected value of y, which is the summation of each value of y times its probability. So 13 hours at 0.04 plus 14 times 0.25, the probability is 0.25 for 14 hours. For 15 hours, it's 0.40, 16 times 0.18, and so on and so forth. So the average evacuation time is 15.14 hours. And then standard deviation or variance will work like this. Sigma squared will be expected value of y minus mu whole squared times probability of each y. So this can be used as a formula here. So take each value of y, subtract the mean from it, square it, and multiply with its probability. So 13 minus 15.14 whole squared times 0.04 plus 14 minus 15.14, and so on and so forth for all values of y. That gives us a variance of 1.2404 and a standard deviation, which is the square root of 1.2404, 1.11 hours. So the mean is 15.14 hours. Standard deviation is 1.11 hours. Okay. Now expected time, let's use the empirical rule. So let's say the evacuation time would be within 2 standard deviations. That includes 95% of the distribution. Okay. So using that 2 sigma range, mu plus and minus 2 sigma will be 15.14 plus and minus 2 times the standard deviation of 1.11. So the range is 12.92 through 17.36. So the evacuation time will be between 12.92 hours and 17.36 hours. Now let's compare it with what the actual probability will be, because we don't know if it's a normal distribution, right? So based on the numbers, it falls between 12.92 and 17.36. So the possible values are 13, 14, 15, 16, or 17. And if we add the probabilities associated with these values, it gives us 0.97. Okay, so 97% chance that, or the probability that the evacuation times is within 2 standard deviation is 97%. Okay, so this is in general the idea of a discrete distribution. We will look at specific examples in the next lecture. We will look at the Bernoulli trial, the binomial distribution, and the Poisson distribution. There are many other discrete distributions which are based on specific properties of experiments. Thanks for watching, and look for the next video on binomial distribution.